So we'll start with module 2, which is generation system model. And today's class we will discuss two parts because this is a very small one. We will discuss generation system model and also we will discuss the basic failure data analysis method, okay, which has no direct relation with power system reliability, but the frequency and duration approach is some way related to that part. So far we have seen this model. Okay. So far we have seen this model. So we have got the generation model. What is that? This is known as capacity outlet. So far the generation model that we have used is a probabilistic model known as the capacity outlet, where you have got various capacities and their probability. Okay. The second one is the load model. Load model can be daily peak load variation curve, or it can also be an LDC, load duration curve, that we have seen. Now when you combine both, we get the risk model, and from the risk model we get risk indices. So what are the risk indices? Loss of load expectation, loss of energy, and also we get something like energy index of reliability. Okay, so this is what we have covered so far. Okay. And a typical generator for reliability analysis is given by a simple model. You have a generator which is supplying the system load. In normal power system analysis, we generally go for a single line diagram, okay, with infinite bus, PQ output and all those things. But here we are only concerned about the generator and the load that it is supplying. Okay. Did you draw it? Draw it. These are supposed to be covered at the very beginning, but now it seems more relevant. Okay. Because we have already studied about all these parts. Okay. Done? Okay. Now, so far we have used the term forced outage rate. Okay, this is without exactly going into the details of what is FOR, we have simply used FOR 0.02 and 0.01. We have used as FOR. Okay, so this is basically forced outage rate is basically unavailable. Okay, FOR is basically unavailable, and this is generally given as downtime divided by downtime plus uptime, also represented as lambda by lambda plus mu. Okay, where lambda is the failure rate and mu is the repair rate. So lambda is the expected failure rate, mu is the expected repair rate. What is exactly failure rate and repair rate? We will see in the next lesson, lesson 10. So M is the mean time to failure, R is the mean time to repair, M plus R is the mean time between failures, and F is the cycle frequency. So these terms are very important. MTTF, MTTR, and MTBF. Mean time to failure, mean time to repair, mean time between failures. So mention these terms. Okay. Just mention the terms. Write FOR is equal to lambda by lambda plus mu. Just write lambda expected failure rate, mu expected repair rate, mean time to failure is given by 1 by lambda, and mean time to repair is given by 1 by mu. Okay, and that is a term which is mean time between failures. So write it down. Done? Okay, I'll go to the next slide. What is availability? forced average rate. Okay, so that was lambda by lambda plus mu. This is mu by lambda plus mu. Okay, you need not write it. Now, this we will see in detail when we see lesson 11 Markov models. But here this is a case. So you can have two-state or a four-state model. So in the two-state model, what you see? In the two-state model, what you see here? You see that you have two conditions. Either the unit is up, which is given by 0, either the unit is down. Now when the unit will be down, when it is failed. So therefore, from up unit, using failure rate, we will go to the unit down condition. And when the unit is repaired, we again come back to the up state. So lambda is the repair rate, mu is the failure rate. Sorry, mu is the repair rate, and lambda is the failure rate. Okay. Now this is a four-state model. So here only two states, up or down. But here it is a four-state model. So in the first case, it is result is not on, it is shut down. That is generator is available. Okay. The second one is forced out but not needed. It is forced out but it's not required. The generator is not required. There is no load. Okay. The third state is forced out in the period of need. That means it is actually out. Okay. And fourth one is last one is in service. Okay. Now various parameters lambda you did not draw this. We will see the bigger model of this later. Only draw this two-state model. Okay. And various rates with which or various probabilities with which you can go to the next state. These are basically Markov models, which will be discussed in detail in lesson 11. Okay. So you just only see this two-state model, which lambda and mu, failure rate and repair rate. Okay. Unit up, unit down, 0. Now what are those? Whatever I have explained, the simple two-state model is adequate for generating equipment of relatively long operating cycles. So for our case, two-state model is sufficient. The four-state model takes care of the situation when the demand cycle, as in the case of peaking or intermediate operating unit, is relatively short, just like hydro units or gas units, okay, where it is used only for peak load. Such units have many startups and shutdowns, hydro units, okay, gas turbines. The following sequence are used. This you need to mention. Just mention. So what is T? T is the average shutdown time between periods of need. D is the average in service time for application of demand. PS is the probability of static failure. So just mention these three terms. Write those terms. Now this is the one problem that I have obtained from the Billington book, reliability, power system reliability. So just go through it. It's not required as such. Just go through it later. The purpose is to give you some estimate of numerical values of availability, unavailability, or how FOR is calculated. Okay, so the example is given here. Service time, available time, okay, number of outages, all these things are there. So all the terms that you have seen, for example, this is how FOR is calculated, how the FOR is obtained. Okay, this example shows that. This won't come in the exam, this is only for your reference. So this part, lesson 9, basically I introduced you to how these terms like failure rate, repair rate, MTBF, MTTF are applied to generation system reliability. Okay, then we will go to the Markov model, that is how the unit states are connected, and the third part we will apply a frequency and duration method to evaluate the reliability. So far we have applied the probabilistic method, that is the capacity outage table, but next what we are going to see is a frequency duration approach based model, not COD. Okay, fine. So we'll see now. So to bridge the gap, to apply this frequency duration approach, we will see the hazard, the failure. So that this lesson 10. So we are going to see failure data analysis. So this I have taken from this LS Vinar book. Typical reliability engineering, mostly dealt by mechanical engineering people. Okay, but this gives all the basics of reliability. So we will discuss only this part. Okay, which is relevant to this module 2, frequency and duration analysis. The definition of reliability, what is reliability? It says that the definition of reliability states that it is the probability of a device giving satisfactory performance for a specified period under specific operating conditions. When a unit or system does not perform satisfactorily, it is said to have failed. Okay. The pattern of failure can be obtained from the live test result. So how to obtain the pattern of failure? From the live test result. As with electronic equipment and various components, for example, the mobile component that you are using, so many components they test and then find the reliability. Okay, that is why testing a fairly large number of models until failure occurs. So, for example, if somebody is giving you a software for free, actually they are testing it. Okay, they are benefiting from it. So when you use the software in white, for example, there is a new messaging app, nobody uses that, then that messaging app cannot be performed. But if large number of users use that, over the period, the company will know the defects in the app and it will correct it. Okay, so any engineering design takes time to mature, and many users should be there. Okay, for example, when Geo network was initially there, it was free. It was free for all. Okay, so by that they tested their whole system. Okay, and since it was free, no complaint can be raised. Because it's free, they are not getting any money for them. Okay, so you need live test result, real test, by testing fairly large number of models until failure occurs and observing the failure rate characteristics as a function of time. The first step therefore is to link reliability with experimental and field failure data. This data will also provide a basis for formulating or constructing mathematically a failure model. Okay. Failure model. So as I said, I have taken the whole PPT presentation from this book. Now we see how the failure data looks like. So one example is from that book only. So consider a series of tests conducted under certain stipulated conditions over 1000 electronic components. So number of components is 1000. Total number of components. Total duration is 19 hours. Okay. The number of components that fail during each hourly interval is noted. Each hourly interval is noted. Okay. I provide developed an Excel sheet for this. I will show you. Suppose delta t is the time interval, that is 1 hour, 19 hours are there, delta t is 1 hour. F is the number of failures occurring in that interval, and F is the cumulative failures up to 7 hours. During the first interval, 130 components fail, leaving 870 survivors. First and second hour, additional 87 components fail, leaving 787 survivors, and so on. We'll see in the next slide. The cumulative failures for the total number of components fail from the beginning of the test till a particular time is given in column 3. We'll see in the next slide. Based on the failure data, our objective is to obtain, you just mention these terms, only mention these 4 terms: failure density, failure rate, reliability, and probability. So these, from failure data, we are actually, our objective is to obtain this 4 terms. Write it down, mention these 4 terms, only these 4 terms you mention. So did you mention those terms? Okay. Now see this in the next slide. So this is the data. So total number of duration up to 19 hours. Okay. In the first hour, 130 components fail. What is the survival? Survival is 870, 1000 minus 130. What is the cumulative failure? Of course 130, because only first hour is there. Then these terms, how they are calculated, we will give the formula in the next slide. Failure density, failure rate, and reliability. According to the failure occurs, every hour so many failures occur. And after, what are the cumulative failures? For example, first hour 130, second hour 130 plus 83, third hour 130 plus 83 plus 75, fourth hour 130, 83, 75, 68, and so on. Okay. Number of survivors is simply 130, 1000 minus 130, 870 minus 230, 787 minus 28, and so on. Okay. These are the number of survivors. So let me check if I have given you the Excel sheet or not. Yes. This is the data. So I have written formulas for everything. So this is cumulative failures. You will simply add up. Okay. I'm simply adding up using the formula cumulative failures. Number of survivors nothing plus D3. I have given dollar means when I drag it don't change because total is same D3. Okay. So like this. Okay. Failure density, that is the formula. Okay. D7 by D3. D7 means this one, D column. Total number of failures divided by total available component. So that is failure density. Okay. What is failure rate? Failure rate is again number of failures divided by the average population in the previous interval and the current interval. F6 plus F7 by 2. Okay, that means F6 plus F7 divided by 2. That means what is the average number of population in the two immediate between the immediate intervals. Okay, that is the failure rate. The reliability is simply given by number of survivors divided by total. So what is reliability? Is basically number of survivors. Okay, which are performing well. Then we can plot. Okay, so all this data can be plotted. So this is how the failure density versus time interval looks like. Okay. This is how the failure rate looks like. Okay. And this is how the reliability looks like. Okay. Now this hazard rate or failure rate that you are seeing here, now when you take more number of components, then it resembles a curve known as the batch curve curve. Okay, which is a very important curve in reliability analysis. Okay. That we'll see in detail. So next is what is failure density. Okay. Write down the definition of failure density. It is the ratio of average population between the interval that I have shown you in the SLC. Write down the definition of halo rate. Okay, so we have written the definition of halo density. Now write the definition of halo rate. What is halo rate? And this failure rate is also known as hazard rate or instantaneous failure rate. Okay. Just mention the definition because calculation I have already explained to you. Next one is reliability. We have already seen the definition, we will again see. So this is the ratio of survivors at any given time to the total initial population. This is another way to define reliability. Write down this. This is the ratio of survivors at any given time to the total initial population. So this is shown how it is calculated. So the important point to note is that as the test proceeds, most components fail, with the result that the reliability factor decreases progressively. Okay, that means as time passes, the reliability is actually reduced. Okay, the reliability factors so often are also called probabilities of survival in the first hour, second hour. The concept of probability of failure is similar to that of probability of survival. This is the number of units failed within a certain time to the population. The term unreliability factor can also be used for probability failure. Okay, just write the reliability definition. Now this, all these things goes to a general result that we will see towards the end of the slide presentation. Did you write the first one? Okay. Fine. Next question. Now these three terms that we saw in the last slide. Okay. MTTF, MTBF, and so on. So what is mean failure rate? This you write. This you have to write. So what is mean failure rate? So mean failure rate is divided by total failures divided by the total time interval. That means every interval, what is the total number of failures divided by 19. Total number of interval here is 19. So it was 19 hours. So the average mean failure rate is divided by this. Mean time to failure for the N specimen is what is the, suppose first component takes 5 hours to fail, second component takes 10 hours to fail. So likewise for all the components, what is the average time to failure? That is known as mean time to failure. What is mean time between failures? It refers to the average time of breakdown until the device is reorganized. And mean time between failures is only used in case of repairable systems when you can immediately repair, just like generators. In our generator case, when generator is out, we can simply go and repair something, suppose the fuel system or maybe something with the prime mover. If something is happening, we can again put back to service. So in that case, we can say it's repaired. Okay, but there are many components which are not repaired. It's not possible. You simply need to throw them. You need to replace them. Okay, maybe air can engines. Okay, they may not be repaired, or it's very risky to repair them. But generators are repairable. You don't throw away a generator just because it has shut down. Okay, you repair it. Okay, so did you write these three terms? Okay. Okay. Now these are the plots I have shown you. These are directly from the Excel sheet. Failure density. Okay. This for the data that we are using. Then failure rate. See, as the time passes, the failure rate increases because components become older and reliability decreases as the time passes. Okay. Now, how to generalize that? So, as you see here, these are some general curves. One is failure density versus time. One is the reliability, which is decreasing. And finally, the very important curve in reliability engineering, which you can apply to any sphere of life. Okay. For example, you consider your say two-wheeler. Okay. So there will be initially infant failure. For first year they give warranty. Okay. So if some failures occur, that means it's a manufacturing defect. So there are known as infant failures. So that's why they give warranty. It's their responsibility. But once it passes that time, that warranty period, that's why they say that warranty is applicable only when service is done regularly. Okay. Second part is service failures. Now, suppose your bike has performed well for first 3 months, then it is extremely unlikely that it will fail during the year. But beyond that, you need to service it regularly. If you don't service it, it will fail. So that's why these are known as service failure. So the failure rate or the hazard rate becomes constant till the service failure. For example, you purchase a car and you have driven it for 10 years with regular service, so you don't break down. Okay. So the failure it occurs only because of negligence, not because of component failure. But then beyond this, beyond certain period known as the wear out failures. For example, if you have a car which is 15-year-old, you say that I will extend my registration and continue using it, then mostly your car may fail or break down, not because you have not serviced it, but because the components are old now. Okay. They are old, they are more likely to fail. Okay. Similarly, it applies to your own personal life also. For example, initial phase during a new assignment, you may fail. But if you succeed that new initial phase, after that, it only depends on your capability. But then, just like suppose you are too old, suppose you are already become 30, then you lose interest in studying for competitive exams. Because that is the last part. Your components are no longer suited for preparing for competitive exams. So it is better to get into a job before 30. These are it. See, you can apply this curve to any field that you want. Okay. So now we will see the explanation for this. So there are three clear zones. The first is the infant or early failure. This period is the breaking period when the components fail due to defects in manufacturing. So these are manufacturing defects. So you can do anything about it. That's why they give warranty. That's why they give warranty. Okay. They inherently weak because of the weak parts. Inherently weak. Manufacturing problem. Nothing can be done about it. Bad assembly, poor installation, and so on. The failures in the second year are service failures. During this period, the failure or hazard rate is constant. The failures are random and fairly evenly distributed. The failure density curve for this period is exponential. Okay. This is to be derived. I have not derived it. Not required for us. Third case is these are wear out failures. Okay. The incidence of failure in this zone is high since most of the components will have exceeded their service life and consequently you have there is a service life. Everything cannot be used infinitely. Okay, there is always a service life for everything. So with this we conclude this lesson. Next class we will see markup problems. Yes.
So why is the failure rate for initial failure is higher than the failure rate for service failure?
Which one? This one? Why the
failure rate for initial failure is higher than the service failure?
Yes, it says that suppose there is a manufacturing defect, you have purchased a car, it is a manufacturing defect. On the very first time you are going for a long, it will fail. Right? So initial failures are high if there is a manufacturing defect. Beyond that means rates are less. Okay. If something has to fail, it will fail at the beginning or at the end. In between it won't fail. Okay. So there is no point of extended warranty. Right? If you say extended warranty, it is actually beneficial to that. Because if your car has not failed during warranty period, it is not going to fail beyond that. Okay. And they won't extend the warranty for this period. Wherever. because they know the system. Okay. Okay. Stop.